Yes.
Sir, could you please share the syllabus for the course in the classroom?
Yeah, the syllabus is there. I'll share it today itself. Okay.
Thank you.
Sorry for that. Yeah. Um,
Sir, by when will we get our first trimester result?
I think in a week's time maximum from now. I think next week you should be getting it.
Okay.
And I think some of the placements are also getting lined up. So I'm sure you guys are following up with that timely.
Sir, just another thing to raise. I
Yeah,
think it would be great if you can say to it. Actually, I raised it in the before class also. Uh,
right.
there might be classes where I personally, on Sundays, I might not be able to join. So
Okay.
please don't make
Okay.
it mandatory. Like it is done in machine learning class that they are monitoring the attendance. So it will
Okay.
be very difficult. So if you can please talk to the instructor
Okay.
once.
But they must be monitoring the attendance, but um, just ensure that the attendance is not part of the grading, because it's in triple IT. What happens is the teacher can decide whether the attendance is part of the grading or not. So talk to the teacher, because it doesn't matter if the attendance is taken as long as it is not part of the grading. And also write an email to the faculty, concerned faculty, that this is an online program, and we are not, we sometimes just, and we are all working, right? Most of us are working, and therefore you may not. Oh, attendance is 10%. Okay, so that has to be. Let me talk to who is teaching that, Janendra, right?
Yeah, sir.
Actually, the easiest thing is you guys should speak to him, ना? तो आपने बोला उसको, ज्ञानेंद्र को?
नहीं मैंने तो अमन सर को बोला
नहीं
फिर
नहीं,
आपको
अमन को
बोला
नहीं, ज्ञानेंद्र को बोलो कि देखो, हम लोग ये रिकॉर्डिंग इसलिए शेयर किया जाता है कि यू विल बी, you guys are working, a lot of you are working, and you can sometimes होता है, मतलब स्टूडेंट्स शुड डायरेक्टली टॉक टू द फैकल्टीज. दिस इज द ट्रिपल आईटी कल्चर. उसमें अगर प्रॉब्लम हो रहा है, देन यू कम बैक टू मी एंड देन यू जस्ट ड्रॉप ए ईमेल ना, सबको कॉपी करके या व्हाटएवर. जस्ट
ओके
ए
सर
ईमेल ड्रॉप कर दो कि ये 10% अब हटा दो, बिकॉज दैट विल लैंड अस इन ट्रबल, बिकॉज वी मे नॉट जॉइन एवरी टाइम. ठीक है.
श्योर थैंक्स अ लॉट
और क्या है, ऑल्सो देयर इज एन अटेंडेंस क्विज at any time. Attendance quiz. Okay. Well, so I think
No, doctor. Can I talk?
yes. Tell me.
No, doctor. Actually, the attendance he may only if we answer that particular quiz, he will mark us present. It seems.
Okay.
Yeah.
Oh, I see. I mean, so it is linked to attendance, right? So he wants to just ensure
Yeah.
that you guys are seriously following the classes.
Yes. Yes. Yes.
But what is important is just to let him know that some of you might not be present all the time because you are working.
Yes,
Sometimes you are
sir.
working on the weekends also, so it could
Yes,
be
sir.
difficult. So just
Yeah.
tell him that. And if it
Okay.
doesn't work, then let me know. Okay. Now,
Okay, sir. Thank
coming back to today's class, I want to teach you something very simple today, but something extremely useful. And sorry for missing the last class. There was some issue. I'll try to share a recorded lecture in lieu of that. Okay. So let me just give you a background.
Sir,
Yeah.
sir, could you please increase the font size of this?
Okay. I can do that too. I think it is pretty big already, isn't it? Can't you
Yes, sir. No,
see?
it's visible. No, it's visible. Sir. Okay, sir.
Yeah, but if it is too big, I cannot write. Okay, so look, outlier detection, outlier out. Okay, sorry. This why it is getting continuous. Sorry. I did it. I made it too big actually. Okay, so outlier detection. It is a data mining problem, and there are several applications. What it means is your data is often high dimensional, right? You must have understood what is dimension of a data, right? Your data could be either also single dimensional data, right? For example, if you are measuring age, that is a single dimension. If you are measuring age, sex, and height, and a lot of other things, that's a very different kind of a data. So where you have multiple variables, you can have thousands of such variables. Nowadays, you have very, very large data in both dimensions. One is the sample size part, sample size or number of data points. Another is the features or variables, right? So the data are high dimensional in both ways, this way and this way, row wise and column wise both. So detecting outliers means detecting anomalies as well. So anomaly or outlier detection are pretty much the same things and have huge applications in the industry. You can use it for finding fraud. Now let's say there is a credit card company. Oh, oh, what's going on? Sorry, guys. I don't know what happened. Credit card or debit card, right? So by the way, fraud is a $18 billion industry as per government record in India, and it could be bigger than it. So I'm talking about India alone. So that's the size of the fraud as an industry or whatever. And so that's one example. The another example could be network intrusion. Okay, so sometimes intrusion also can be detected using outliers. So if you have such a network, like, I'm talking about your LAN or your internet, so there could be such intrusions into the network which are malicious, and they should be prohibited. And for that, you need to be able to detect them. And the way you detect it is using outlier detection. Okay. So there are multiple things that you can do. For example, finding a rare disease, right? So something that is rare, that has been observed very less number of times, right, previously, or maybe never, that can be categorized as fraud or anomaly, or not fraud, I mean anomaly or outlier detection. So now today we'll learn about a couple of methods for anomaly or outlier detection, which are very simple. The first one we'll talk about is the box plot based method. Second, we'll talk about, so this is univariate, right? Univariate. How you can use box diagram to identify the outliers. Then under multivariate means that can variate, that can deal with multiple variables. We'll talk about fire, that is our own algorithm. So our lab, currently, I think one of the best methods in the market. And we'll talk about HBOS, right? We'll see the theoretical aspects of them, and we'll also, after towards the end assignment, but that is going to be very, very simple given that you understand what I am teaching now. Okay. So let's follow. And if you don't understand, just come back to me and ask me question by unmuting yourself. So when you have a data, when you are given with the data, and I will do some exercises with you, like what do you do when you get a data in industry? So you need to do a storytelling, you need to do some pre-processing, pre-processing, and exploratory data analysis, right? Data analysis, and you need to do machine learning, right, or stat. So these are the three things pretty much you do. And under the pre-processing part, you do a couple of things which are very important for you to know from a theoretical point of view. One is outlier detection. Another is missing value imputation. Missing value imputation. Actually, my lab has worked on both these problems quite extensively. You can check out my paper on the Google Scholar or elsewhere. Okay, so when it comes to exploratory data analysis, you need to know statistical methods. Statistical methods like how do you look at the distribution? How do you do different statistical tests like chi-square test and all that? I think some of that must have been taught in the statistics class. And so on and so forth. Then ML stat, where you do basically clustering, classification. I mean, I'm writing fast, so my handwriting is very bad. So bear with me. So this is pretty much what data science is all about, right? And exploratory data analysis is better known as storytelling, right? You will have to, given a data, you will have to tell a story with the data, that what are the possibilities, what are the indications, like what are the associations that coming up, what are the correlations that you can observe between the variables and the different classes. So even before getting into the black box modeling, you can typically talk about how the associations of the different variables look like. Okay, so that's pretty much what data science looks like. So today we'll focus on only one item in today's class. So that is outlier detection. And I have already told you outlier detection could be of two types. One single variable, another is multivariate. Okay. So let us first see how the single variate, the univariate approach works. So I think all of you know how the box plot is drawn. So if you have some data points, you can define the quartiles, right, or quantiles. Okay, that means, so what is 25 percentile, right? So that is the value which defines the first, which defines the lower bound of the first 25% of the values of the variable that you have observed. If you look at 50% and then 75%, and so on and so forth, right? So no matter how many data points you have, like I can have 1,000 data points. Okay, so that means if I ordered them, the 25 percentile will be the 250th item and its value. Okay, so the idea of quartile is very simple, which has nothing to do with how many data points you particularly have. So quartiles, basically, for example, if I have 1,000 values given to me, what I can do is I can sort them in increasing order, which means if I have 5, 3, 8, 19, 77, right? So I can order them as 3, 5, 8, 19, 77. And then I can ask that what is 25%. So you should find out 25% of 5, right? So how many numbers that translates into? It's 1.25 or something like that in this case. So this could be your, or I mean, of course, this is a toy example. You will have much more data points. And therefore, the 25 percentile will mean that 25% data point and that its value. So that will define you the 25 percentile of the observation. Okay, so that you can see has nothing to do with how many data points you have. It is agnostic of the total number of data points. It has to do with the percentage. So in this way, you can define the following quartiles, right? Or percentile, whatever you call it. Okay. And here, as you can see, this is the 25th percentile, and this is the 75th percentile. Okay, and then this is the 50th, right? So this is 50th percentile. Okay, but then how do you define these things? How do you define the this bars, which beyond which, if any point lies, you can call them outliers? So the difference between the Q1 and Q3 is regarded as interquartile range. Okay, so this is an absolute difference between Q1 and Q3. Q1 is a value, Q3 is a value. Q1 is the 25th percentile value. Q3 is the 75th percentile value. Their differences will be called interquartile range, IQR. And the way you can define the bounds for the outlier detection is following. The minimum will be Q1 minus 1.5 times interquartile region, Q3 plus 1.5 times interquartile region. Very, very simple and easy to remember and implement. And now you can say that anything that falls beyond this maximum value, right, that is outliers. And similarly, if it is below this minimum value, then it will be called an outlier. So the outliers can fall on both sides beyond the extreme limits that you have set for your data. I hope it is clear. If you have question, you can ask me.
Sir, please repeat the Q1 minus 1.5 IQR. What does this mean, sir?
So that's a, see, Q1 is here, right? This is, let's say, Q1. And this is the this is the Q1. Q1 is your 25th percentile, right? So if you have 100 different values, and if you order them, then 25th value will be your Q1, right? And similarly,
Okay, sir.
75th value will be your Q3. Just imagine that these values are ordered, because when you draw them like this as a box plot, had you just plotted each and every point, then visually they will be ordered, right? If you plot them sequentially, they will be ordered, at least visually. Now, if you define the Q1 as the 25th percentile value, so if you have 100 data points, then 25% will be 25. If you have 1,000, it will be 250. If you have 750 data points, this will be 750 times 25%, whatever is that number, will be your Q1, right? And similarly, 750 times 75% will be your Q3. Okay. Now you will get some absolute values there. You will get some, because this number will, like, just to clarify it even further, just take, sorry, I don't know what's going on. Let me, okay. So just take an example like 5, 3, 19, 17, 27, 33, 12, 8, 1, 2, 3, 4, 5, 6, 7, 19, 2. Okay. So these are your values that you have observed. Now what you can do is you can order them. So if I order them, it will be 2, 3, 5, 19 दो बार आ गया, that is fine. Then it will be 12, 17, 19, 19, और क्या रह गया, थर्ड
Sir,
12.
eight
Sir,
also
8
after 5.
after 5.
Yes, and 22, 27, 33. So these are 10 values, right? So 25th percentile will be what? What will be 25th percentile?
2.5.
25th percentile of, so which one? You can just, for example, take this, okay? And you can take, for example, this, and you can say this is your Q1. Of course, you will have a lot more values, so it doesn't matter here and there if you just go one step ahead or one step back. So the difference will be maximum of 1 digit, because you cannot pick up 2.5th position. You can either take 3 or you can take 2. So let's say you define this as Q3 and this as Q1. So the interquartile region will be 19 minus 5. And that will be, it's a mod of that, right? So that will be interquartile region. And that will be 14. Okay. So then it will be Q1 minus, so the left bound will be Q1 minus 1.5 times IQR. So this is your IQR. That means you can find it out that 5 minus 1.5 times 14 is going to be your lower bound. And similarly, you can find out Q3, because you know Q3 is 19, 1.5 times IQR is your upper bound. So at the end of the day, your box plot will look like this. This is 50th percentile. This is 25th percentile. This is 75th percentile. And you will find further two extreme bars telling you that anything falls beyond this or below this will be an outlier. Is that clear to all?
Yes, sir.
Okay, fantastic. Let us move on. This is just very simple thing, but very useful thing. This is foundation of many important discoveries. Today we'll do something very novel in our assignment. Okay, so let's see how it pans out. So now look at this HBOS method. This is one of the best practice methods, yet it is very simple. It is ridiculously simple, but it's a very established and good algorithm, which is non-parametric and powerful and very, very fast. Okay, so histogram-based outlier score. And you see, after you study this algorithm, you will realize that innovation is not very complicated every time. Sometimes very simple methods give you very useful algorithm. Let's see how it works. So, so how your matrix looks like? Your matrix looks like this. You have some features and you have some samples, right? So one big problem of multivariate data analysis is that you need to sometimes, for the simplicity of the method, you need to assume conditional independence. Conditional independence. What does it mean? In simple terms, it means that your variables are independent. Have you been taught naive-Bayes algorithm in machine learning?
Yes, sir.
Fantastic. So one weakness of naive Bayes is that um, your variables are considered independent, are considered independent, but that is not really true, right? You treat the variables independent, but you know in your heart that all these variables could be, some of them could be interconnected with others. But if you take that into account, then your methods become really cumbersome. Okay, so this is another method which does this dramatic assumption, which makes this assumption that none of my variables has to do anything with the other variables. So what you do is you basically take each one feature at a time, one feature at a time. That means one column of the matrix at a time, and you draw a histogram. Virtually, you draw a histogram. I don't know why there is a lag in my pen and it coming up, and no idea. But anyway, so so you draw a histogram for each of the variables. Like you draw it for feature one, you can draw a similar for the feature two, and the similar for the feature three. I'm just telling you the intuition. You draw this kind of histogram for each feature. So each bar comprises some data points, right? Some data points of some of your data points will fall in this category. Some of your data points will fall in here. Some of your data points will fall in here, and so on, so forth, so on, so forth, right? Now, what you
Sir,
could,
are
yeah.
you showing something on the screen? Because we don't. You were saying that you could draw it here and there, but we don't see the screen. In fact.
Since when you can't see the screen?
We were seeing that histogram. I mean, there's a description, right? We see that screen, but not the one I think which you are using right now. I guess.
No, no,
No,
screen
can
is
you?
visible.
No, I am just showing the whiteboard, nothing else. I am just, you can see this, right?
Yeah, that's visible. But I was thinking maybe I think you were drawing it somewhere else on the board, which is
No,
not
no,
visible to us.
no, this is I am drawing now. Can you see my drawing?
Yes, I can see now.
Okay. Let's say you draw a histogram like this for feature one, and you draw another histogram for feature two, right? So this is feature two. You have been given a very simple data. Just imagine that you have been given some, let's say this is weight and this is height. Just that you have been given weight and height, and you have considered the weight and height for at least let's say 1 million people. Now, who will be the outliers here? For example, a basketball player will be basketball player will have a very high weight value, high height, and let's say wrestler will have a lot of weight, right? So, and let's say somebody who is dwarf, or somebody who is like Kali, gigantic, this will be some of the people who will come up as outliers, right? Now, now what will happen if somebody is outlier and somebody is a common man? Common man. So let's say in the weight, the guy who is wrestler, Okay, so the guy who is wrestler will fall because this is the weight dimension and this is the height dimension. So most likely the guy who is wrestler will fall within this box somewhere. He will be counted as part of this box. But what do you observe here? It is a very simple observation that the bar it belongs to has very few samples in it because it is extremely rare. It could also be here somewhere. So you can say, okay, so I have two wrestlers, both are here. Okay, similarly, you can have a dwarf man whose height is very less, it's here, right? So, what this H boss guys realized is that a simple way to assign a score to a rare event is just by looking at in which bar it lies, in which bar it lies, right? And how many elements are there in that bar. If it is less, then it is rare. At least for this feature, this event is rare. At least for this feature, this event is rare. And now you need to combine these things somehow because you can imagine that the dwarf guy will eventually have lesser weight also. Maybe he will come somewhere here. It will not be absolutely rare, but maybe he comes here. So overall, for a rare guy, it could be just one feature extremely different, or it could be many features out of all features which are different. So there has to be a way by which you can integrate all these rareness values. And here the surrogate for the rareness is the height of the bar. Now tell me something, guys, that what is the difference between a histogram and a density plot? Can somebody tell me? What is the fundamental difference between a histogram and a density plot, and which one is useful? Which one is more mathematically correct?
Is density plot more correct in the sense that the probabilities, the maximum height would be 1.
Yes, yes. So you can compare two distributions. If you have density plot, then let's say it looks like this. So the overall the area, if you do an integration of the probability density function, p of x dx from minus infinity to plus infinity, it will be 1. So it is normalized. Histogram is not normalized. Histogram is just count number. So the y-axis for a histogram is just number. So if you are measuring height, now I'll tell you where is the problem. Let's say you are measuring height, I am also measuring height. I measured for 100 people, you measured for 10,000 people. Now both of us measured of the same population. So if somebody else measures 1 million people's height, all our histograms will look very different. Our histograms will look very different because the size of the histograms, my size will be this, your size will be this, somebody else's size will be this. It's very hard for somebody to compare the histograms when you have different number of values, different number of observations which have gone into it. But all of us, if we draw the density diagram, then it will more or less look similar. So it's a very powerful thing, isn't it? It's a very powerful thing. So for this 100, 10,000 and 1 million, pretty much the dendrograms will, the density plots, the probability density plots will look the similar. Just think about this when you go back. Now, but imagine what will happen here if I just consider density plot. Density plot, it's very hard to find out the height at a given point. It's possible, but it is complicated process. You need to do a lot of smoothing and all. And also the problem is in the density plot, there is one big problem that you need to know how you will smooth it out. You need to pretty much apply some parametric methods to come up with a smooth representation of a continuous variable, right? But you can use Gaussian or something, but that will not be necessarily applicable to all the features. So histogram is very powerful because it doesn't have a parameter. It's non-parametric. You just count the number of events, number of observations within a given range. So that's powerful. So what you can do is you can settle down at a midway. You can simply divide let's say the total number of people I have here is 12, here 33, here 27, here something else. All that you do is you add them all and divide this number by that addition, by the sum. So then if you add all of these numbers, you add all these fractions, because then they will become fractions. And once you add all the fraction, it will become 1. So it is comparable. It's absolutely comparable. Okay. So it's a very, very simple, intuitive way. And this you can consider a histogram can be after dividing by the sum of the total number of values, it can be considered as a probability mass function, right? Like a discrete function where you have some discrete events and you are counting how many times it happened. So it's very simple, right? It's no rocket science, simple ideas. But these simple ideas can be translated into seemingly powerful algorithm, okay? And that is HBoss. So what they say, I don't know why they have written this. I'm not sure. But what they're basically doing is every feature has a range. Like I have 1,000 observation. So I have a range of values. And they're splitting that range into k bins. And they're counting how many points lie in each of these bins. How many points lie in each of these bins? So they're counting that. And of course, they're dividing by the total number. So I don't know the relevance of this. So if somebody can understand what they're trying to say, I think they're giving two options, but this is not meaningful to me. Anyway, at least they must have thought something, but I don't understand that. So basically what they're doing is for every feature, they're creating this histogram, but they're not only creating a histogram, they're creating a normalized histogram, right? So the heights of the bars are divided by the sum of the total number of observations. That's all they're doing for each of the features. So I can call this as a probability. Let's say there are only 15 individuals in this bar. So if I am lying here, so for all the data points here, the probability will be 15 divided by the sum. 15 divided by the sum, isn't it? So for each data point, now you can think like this. Let's say you have just height and weight as features. Height and weight as features. And you have data point 1, data point 2, data point 3, and so on and so forth. So for every feature, you will get a probability. Okay, so if this is the data point 1, then the probability will be 15 by, let's say, 1,000. That will be the probability. Let's say 15 by 1,000. That will be below 1. Okay, and similarly, you will have something here, 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 here. So for every data point, you get multiple probability values based on how many features you are dealing with. Is everybody able to follow what I am saying, or there is any question? I can stop over and wait for your query.
So, sir, just the last part, could you repeat again? I was following until when, let's say, you made this histogram above, And you said that
Okay.
15 is a data point in that last
No, no,
bar.
no, no. 15 is the
Number of points in that
total
bar.
number of data points, which is part of this.
Uh,
Now let's say
okay.
now let's say there is one data point
Okay.
which happens to lie here. For this is, let's say this is the height histogram, and similarly you have a weight histogram. So each data point will lie in one of the bars, right? One of the bins, I should rather say one of the bins. They will lie in one of the bins. For height, they will also lie exclusively in one of the bins of weight. And this is normalized. So I am saying all the points that lie within this bar will have the same probability. That is total size of the bar divided by the sum. Is that clear? The total observation.
Yes, sir.
And similarly, for weight also, you will get a probability. For every data point, depending on the bar height plus the total number of observation. So you will get a probability. So you document all these probabilities, you tabulate all these probabilities, and then you come up with an HBOS score. And this HBOS score is like this. And here comes some interesting observation. Again, very simple. What they're doing is they are taking for every data point, HBOS of a data point, what they're doing is they're coming up for every feature, they're getting a probability. If you have D number of features, so you get D probability values. They're writing it as hist of P, hist I, P. So they are marking each feature as I. I is varying from 0 to D. That means you have D number of features. Each feature is marked as I. And for each of the feature, for each of the data point, you can get a probability value that you are marking as hist I of P. P is a data point here. So it's a bit, bad notations, I would say. P is a bad notation for data point. They should have called D or something like that, and feature for F. But anyway, for P data point, they are looking at the probability that comes from the ith feature histogram, the histogram associated with the ith feature. Okay. And then they invert it. They take 1 by this, because if I take the probability value, so they take 1 by the probability value to get a big number here. They get a big number here because 1 divided by a small number between 0 to 1 will be a big integer, or an integer at least. And then you take a log of that and you add these logs basically. So add them up. This log A plus log B.
Wait, excuse me, sir. Just interrupting once again. This hist I of P, is it the probability or the normalized one? I mean, the divided by the.
Exactly.
It's a
Exactly.
normalized. Okay.
It's the normalized value. I should not call them probability. It is the normalized bar size.
Thanks.
Bar height normalized by the total number of samples is this P. And the I indicates for which feature you get this value. So for a data point, for every feature, you can get a probability value, a value between 0 to 1, 0 to 1. And you are doing this operation, you are taking the log and you are adding them up. Okay. And whatever score you get is your rareness score. Okay. So for an extremely rare item, my question is whether the score will be small or large. What do you think? Yeah.
It should be large.
Yes, very good. Because you are doing 1 by, let's say it's something very, very rare. So 1 by 0.005, versus had it not been that rare, it would be 1 upon zero point 0.5. Now this number becomes large. This number becomes larger than this number. So this is rare, this is abundant in plenty. Therefore, you get a large number if it is rare. And since it is not a fraction, even its log will be a larger number, right? As such, when you add all these numbers together, it will be, in the end of the day, a large number for a rare sample. Fair enough. Very simple algorithm, intuitive, easy to implement, lightning fast. So it works on big data. Any further question I can answer before I go into the next algorithm?
Sir, on this, could you please show the equation?
Equation, okay.
Yeah, I mean formula. Yes. Here, I think I think what I understood is that you said P is the normalized value of a feature.
Yes, P is the normalized value based on, let's say, for a data point, if it is in this bar and then there are only 33 samples which are part of this bar, and there are total 1,000 data points, then every data point that is falling in this, for that feature, it will get 33 by 1,000 as the probability.
Okay, that helps to understand better. Thanks.
Okay. You're super slow.
Sorry, I will mute.
Yeah, that's okay. I'm just a bit curious why it is so bloody slow. um, I'll probably open a new whiteboard. Okay, so the challenges with HBOS. What are the challenges with HBOS? I think there is only one fundamental challenge with HBOS. Can somebody tell me what is that?
Feature independence, you mentioned that.
Yes, assumption of feature independence. So our group back in 2017 was thinking about how we overcome this problem. That how can we look at? So then I came across this seminal work by many scientists. I probably told you about Rajiv Motwani, whose group published a paper on locality sensitive hashing. Sensitive hashing, what it does is it's an approximate nearest neighbor finding algo. And I probably told you before that nearest neighbor finding is probably the most important and fundamental big data mining problem. So guys, nearest neighbor is like when you have too many data points, how quickly you can find, and this is your query data point, how quickly you can find which are the nearby ones. Like you can spot this as nearby and this as nearby. To exactly spot it, you need a very complicated algorithm, but if you want to spot it approximately, you are okay even if you don't spot the exact nearest neighbors, but also, but rather you capture the ones which are pretty nearby and they're good candidates for nearest neighbors. So there comes the idea of approximate nearest neighbor finding, and trust me, that's the most important data mining challenge. So, so this guy invented an idea. He came up with an idea that if I simply, let's say, there are three clusters, and if I draw some hyperplanes randomly, right? So I drew hyperplane 1, hyperplane 2, hyperplane 3, hyperplane 4. If I draw the hyperplanes randomly, then if I just see that whether it is on the left hand side or the right hand side, each data point I can tabulate, let's say data point 1, data point 2, data point 3, H1, hyperplane 1, hyperplane 2, hyperplane 3, hyperplane 4. I can simply document that whether it is on the left hand side of the hyperplane, whether it is the right hand side of the hyperplane. So now let us take a look at these 2 points. Let's say these 2 points, okay? They are apparently part of the same cluster. If I just run a clustering algorithm, then these will be the clusters. These will be the clusters, okay? So ideally, you should be able to identify the nearest neighbors which are part of the same cluster. So now see what is happening. I literally drew all these 4 hyperplanes randomly. I didn't really care how it is happening. So, but even by doing these random operations, we realize that, let's say I call it D1, I call it D2, I call this D3, and this is D4. Now, you look at hyperplane 1, right? So D1 is on the left-hand side of the hyperplane, and you can find it using, but these data points are not two-dimensional. These data points could be n-dimensional. So you can simply do a dot product of the hyperplane and the data. And just based on whether it is greater than 0, then you assign 1. If it is less than 0, you assign 0. So that essentially tells you whether it is on the left-hand side of the hyperplane or the right-hand side of the hyperplane. And you just look at that, and then you put this binary values. Let's say I say this is the left-hand side of the hyperplane, right? And what about D2? D2 is actually on the right-hand side of the hyperplane. The rest of the things are the same. The rest of the things are the same. For the rest of the hyperplanes, they are on the same side. This is the only hyperplane. H1 is probably the only hyperplane which actually cut them off into 2 different spheres. For the rest of the hyperplanes, let's say I just randomly give it, right? I don't see whether it is, they should have the same values. And the same is true for these guys. These guys have the, I'm just randomly putting it, they are always on the same side of all the hyperplanes. So what you notice here is that these 2 guys have a Hamming distance of 1. Only 1 bit they are different. These guys have a Hamming distance of, let's say I put this one as well. These guys have a Hamming distance of 0. But if you compare across these groups, then you will see that they have higher Hamming distance, for example. So even by drawing some random hyperplanes, you will end up getting smaller Hamming distance for ones which are close by. And it actually approximates, so Hamming distance between the bit codes approximate cosine distance. Okay? You understood? So just by drawing these random hyperplanes, you can actually approximate their cosine distance in the original space. wonderful algorithm because this can be implemented also in GPUs, and it will be lightning fast, actually, lightning fast. And the what we did was, you will notice here that this gives a flavor of multivariate stuff, right? You are actually doing a combinatorial coding of the data. Your data must be in 1,000 dimensions, and you are drawing only four hyperplanes. So your data now becomes a 4-bit vector, right? But even then, it is combinatorial. You are looking at multiple dimensions at a time. So typically, we have seen that 10 to 20 bit representation is enough to approximate the data. It is wonderful, right? There's a JL lemma you should look at, which is a breakthrough work in the field of data mining, that you really need very small amount of information to understand the structure of the data. That's a lot more theoretical, and it will be a waste of time if we do that here. I don't think we have the right mathematical background to be able to understand that, and it's not essential as well. It's for theoretical researchers. Now you look at our algorithm. What we said was, if I have some data points like this, let's say the black ones are the rare, the pink ones are the abundant ones, the yellow ones are the abundant ones, and these ones are again rare, right? So we have some rare populations and some abundant populations. So what we do is we draw these hyperplanes multiple times. So each of these, so if I draw hyperplanes, I create some cubicles, right? 1, 2, 3, 4, 5, 6, 7. 7 cubicles are created. Okay, so this picture actually just shows all these cubicles. I mean, it's a graphical abstract. It is not the exact thing, but this is telling you that how it happens. So these data points are rare. So once you hash them, so you draw one set of hyperplanes, you draw another set of hyperplanes here, you draw another set of hyperplanes here. So you hash them multiple times. And just like histograms, you have cubicles here, beans here. But these beans are not univariate beans, they are multivariate beans. That was the fundamental difference of us with HBOS. So each of these beans is created by multiple hyperplanes taken together. And we counted the total number of data points in each of this cubicle, and we divided by the overall number. So we showed this application on cells. So cells in a bucket and total number of cells is the probability that is assigned to all the data points in this cubicle. This is the probability assigned to all the data points in this cubicle. And you see that in this cubicle, you have far less data point because it's a rare zone. So this cubicle is not capturing abundant cell types. And finally, what we did was exactly what HBOS, but we didn't know about HBOS that time, but we pretty much did the same thing, that we use something called Fisher score. We considered this as probabilities, and we added this log of the probabilities for each of the data point, and this is the Fisher's method, that it should be actually chi-square distributed. Sorry, chi-square distributed. Okay, so Fisher score is chi-square distributed. Now, here also we get high values for the max, for the rare ones, and the low values. So that's all. I mean, the critical difference is replacing the histograms by the hash cubicles or the bins. And the rest of the operations are pretty much the same. The formula is slightly different. We used an established formula here, Fisher's method, because it has a known distribution. It follows chi-square distribution. And we sort of explained that beautifully using this toy diagram, and it's published in Nature Com. It's one of the most reputed journal. And clearly, this is if not it is the best, it is one of the top three, I would say today. A lot of papers came after that. So I'd advise you guys to look at it. They're slightly advanced. You can come back and ask me question in the next class. But now, if you don't have, you can ask me if you have question now. If you don't have, then I will define a small assignment for you. I think Namrata is there. Namrata, are you there?
Yes, sir.
Okay. So, guys, the thing that I ask you to do is very simple. Yes, tell me. Okay. So, what we ask is very simple. We ask that you design a new algorithm altogether for the first time in your life. New algo. And what is this new algo? This new algo is something similar to HBoss, but not exactly the same. So what is the new algorithm? If you have a feature versus samples, for every feature, you compute, you draw the box plot, not draw, you just decide that whether the point is outlier or not. Okay. So for every data point, for every feature, because for every feature, because this is one feature across all the data points, you can draw the box plot. And you know that this data point is here as per the box plot. This is beyond the outlier bounds. So then if it is beyond it, then you define 1. Otherwise, you do 0. Okay? And you do it for all the features. And then finally, you add them up. So you will have multiple ones. So basically, you are saying, you are just simply counting in how many cases, in how many of the features, your data point, in how many of the features, your data point is an outlier independently of other features, according to the box method. And you are simply counting the value, you are adding them up, and you are reporting that. And please show if you have, it's so simple, like 3 to 4 lines of code. And you can show in let's say you take iris data, and you plot principal component, you do PCA, plot PC1, PC2, and mark your top 2%, outliers. Okay? Isn't it very simple? What do you think?
Sir, I have one question here.
Yes.
So, in this algorithm that you explained, once we once we assigned 0 or 1 to each data point, every feature,
Yeah.
then when we are counting them, so we would count them across the rows, I mean, across all features.
Okay. Yes, you are right. So let's say this is data point 1, this is feature 1, feature 2, feature 3, feature 4. You decided that the data point, you observed that the data point is outlier according to feature 1, not outlier according to feature 2, 3, but outlier according to feature 4. And you just add them up. So you get 2.
Understood.
And you do it for all the data points, and you just take the top 1%. But this will work better in other, don't use iris, use something else, whatever you like. You can also use iris, it doesn't matter. And show that in PCA plot. Namrata, are you there?
Yes, sir, I'm here.
So please create an assignment submission link explaining this problem roughly. I have explained it already, so they shouldn't have question. Just write outlier detection using box plot, and then create a submission link for them in the next 45 minutes. Okay.
Okay.
Okay, guys. Best of luck. You can ask me questions if you have. Otherwise, I'll push off. I'll be there, but But anyway, so you can ask me a question before embarking on solving this.
So just one clarification regarding PCA part.
Yes.
Once this summation has been done, we are able to find out that how many outliers are there. I mean, bigger this number, bigger that
Yes. Yes.
possibility at the point is the outlier.
Yes.
So in the PCA, what are we doing? I mean, what are
Okay.
we
In the
plotting?
PCA, you show two colors. You show two colors. Let's say this is three clusters, right? So you show all the data points in black color, and you show your outliers in red color. The top 1% of the data you show in red colors. The rare data points you show in red colors. That's all. And this will be your PC1 and PC2. Is that okay?
Sir, the question is, sir. Hello,
Yes.
sir.
Yes.
So so the question is outlier detection using PCA, right?
No, 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 no. The question is outlier detection using box plots. Outlier detection using the box method. I don't think it is available anywhere. You will have to do it yourself. Okay.
No, you were talking about one PCA.
No, 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 no. PCA is just to visualize the rare data points. PCA is just for the visualization. You first need to find out the top summations. And I'm saying the top 1% of your data according to this value. You should plot using some different color in the PCA. You know what is PCA, right?
No, sir.
Yeah.
Yeah, that just show them that where they lie. Visually, are they really looking as outliers? That's the simple question. How you will convince me that you can give me some values, but how can I visually ensure that these values are indeed indicating rare entities which are here and there spread out across the plot? Okay. All right. So I will stop the recording now.
I,
And yes,
I
yes,
posted the assignment.
yes. Thank you.
Excuse me, sir.
Yes.
Sir, can we take help from other sources with regards to the
Yes, yes, yes.
coding? Or
Go ahead, please. Please. No problem.
thank you, sir.
Excuse me, Namrata, are you there?
Yes.
Namrata, could you please explain again what exactly needs to be done?
Like you have to represent the outliers using box plot on the PCA space.
But what is this PCA space like? I have never heard of this term before.
When you are taking the data, it is n-dimensional. So what you do is you do the principal component analysis and you represent it in a PCA space where you can take it like in a
Yeah, but
2D
actually,
format.
the thing is that I don't know how to perform principal component analysis.
Well, have you understood the outlier detection portion of this?
Like whatever was taught.
Yes.
Yeah.
Yeah. So from
Like
there, like,
I'm not very much clear about the HBOS technique. I still need to go through it. But before that, the technique which was explained using box plot, that I understood.
yeah, so you just represent whatever there is using box plots. So for plotting the box plots, you have to bring it in a PCA space, right? You cannot represent it in like n dimensions. You have to like visualize the plots using 2D coordinates.
Yeah, but I can basically for each of the features in the data set, I can uh, plot the box plot, na?
Yes, yes, definitely. Yeah, for each of the data points, you have to plot that. But by PCA space meant that for visualization, for bringing it from n dimensional to two dimensional, you have to do PCA. That's all. Rest is same.
Hello, Namrata.
Yes.
Can you just share the link to upload the quiz or assignment?
Yeah, so I have posted it in the classroom. You go there
Okay,
and you
okay, okay,
check
okay. Done,
assignment 2021.
done, done.
Okay.
Hello, Namrata. Hello.
Yes.
Is it the code or the algorithm that you're looking for?
Sir has asked for the code and the
No,
result.
because I remember Dr. Dibaka was telling that you have to design an algorithm. And is it necessary
So
that we have to write this in Python?
you have to do it in Python, and he was talking about code because without code, how can you represent something? How can you present box plot in the PC space? So,
Okay, okay. Thank you. Thank you.
Uh, excuse me, ma'am. Excuse me, ma'am.